Hello again. This is Math 2232 coming to you from the College of the Page. The title of this lecture is Numerical Integration, Approximating Definite Integrals Using the Trapezoidal Rule and Simpson's Rule, and this is the conclusion of that lecture. Please be attentive as you watch this video. When we left off with the last video, you were working this problem, and if you finished this problem, congratulations. If not, I'll give you a little bit of time now. But you're using the trapezoidal rule and the midpoint rule with n equal 5 to approximate this definite integral from 1 to 2 of 1 over x dx. You know what to do. Let's see how you did. So if you use the trapezoidal rule, you would say that this definite integral is approximately, we call this t sub 5, that's n equal 5, and these are the values that you should be putting in. F again is 1 over x. You substitute in and you should get this. Now notice how closely the lines that I'm drawing with n equal 5 hug the curve y equal 1 over x. So you expect that to be pretty good. This is the midpoint rule. Again, we're doing the midpoint rule. The picture looks a little bit different. Looks like we've got 8 slices, but that's because we're doing the, it looks like we got 10 because we're doing the midpoints, but this is what we get. So n is 5. We're doing the midpoints here now of each interval, and you should get this number. Now this number and the other number aren't the same, but they're close to being the same. And that's okay because both of these were approximations. Now, we deliberately picked an example here where you actually could do this exactly, and the exact answer is the natural logarithm of 2. So this allows us to say, gee, what was the error? An error meaning E-R-R-O-R in using those approximations for n equal 5. So the error in the trapezoidal rule was approximately, and you can see this negative number here. And so we were comparing the actual exact answer with what we got by the trapezoidal rule and the midpoint rule, and here was the error. And you see we're defining the error, E-R-R-O-R, to be the approximation plus the error is the value of the integral. And in this case, we knew the value of the integral, so we could actually come up with this. Now, in general, then, the error with the trapezoidal rule is going to be the exact value of the integral minus t sub n, where n is the trapezoidal rule for this function, f of x, and we're using n steps. And the e sub m is for using the midpoint rule, and again, we're subtracting the midpoint approximation for n. Now, we're going to look a little bit at some results. So the following tables show the results of the calculation similar to those for example 1, but we're letting n be 5, then 10, and 20, and we're comparing the left-hand endpoint, the right-hand endpoint, the trapezoidal rule, and the midpoint rule. And so you can see these are the corresponding approximations, and these are the corresponding errors. And I repeated those up here. But here's some observations that we can make from these tables. In all of the methods, we get more accurate approximations when we increase the value of n. But very large values of n result in so many arithmetic operations that you have to be aware of accumulated round-off error. But as n gets bigger, it gets closer and closer to the results. The errors in the left and right end approximations tend to be up here opposite assigned, and they decrease by a factor of about 2 when we double n. So if you double n, you decrease it by a factor of 2, the error. So it gets better, and that's how quickly it gets better. The trapezoidal and midpoint rules are much more accurate than the endpoint approximation. So these are better things to do. And the errors in the trapezoidal and midpoint rules are opposite in SIGN, sign, and appear to decrease by a factor of about 4 when we double the value of n. So they get better, and they get better faster. And the size of the error in the midpoint rule is about half the size of the error in the trapezoidal rule. Again, you can see this from all of these examples. Now, these observations are in fact collaborated in the following error estimates, which are proved in books on numerical analysis and also in books on advanced calculus, not in calculus 2. Notice that observation 4 corresponds to an n squared in the denominator. That means if you double n, you improve by a factor of 4. And the fact that the estimates depend on the size of the second derivative also is not surprising if you look at the shape of the curve, because f double prime from your calculus 1 measures how much the curve is curved. And so f double prime comes here. So here are error bounds for the midpoint rule and the trapezoidal rule. So suppose that the absolute value of the second derivative of x is less than or equal to k for x between a and b, including the endpoints. So if e of t and e of m are the errors in the trapezoidal and midpoint rules respectively, as we were talking about, then the absolute value of the error in the trapezoidal rule is less than or equal to k times b minus a whole cubed divided by 12n squared. And the error in the midpoint rule, the absolute value of the error in the midpoint rule is less than or equal to k. This is b minus a whole cubed over 24 n squared. So you see they both have n squared in the denominator, and this one is actually better by a factor of 2 because 12 is 1/2 of 24. And if you really want to be doing this, you need to get a handle on k. So let's apply the error estimates of the trapezoidal rule approximation. So if f of x is 1 over x, which it was in the very last example we did, then the first derivative is minus 1 over x squared, and the second derivative is equal to 2 over x squared. Now, because x is between 1 and 2, we have 1 over x is less than 1, so the absolute value of f double prime of x is equal to the absolute value of 2 over x squared, and you can conclude that this is less than or equal to 2. Think about this and make sure you understand why this is true. Now, that means we can take k, which is the maximum of this, to be 2, and so the error in the trapezoidal rule is less than or equal to k is 2, b minus a is 1, 12 is 12, and n was 5. We plug all of that in and we get 1 over 150, or this is a decimal approximation. Now, so what happens in the theory is that the theory for a general f that you can come up with is going to be that k is less than or equal to the max, or is bigger than or equal to the max, where you're letting a run from a to b of f double prime of f of x. And from Calc 1, you know that if f double prime is continuous, that there in fact is a match. But even though this is theoretical, often in practice, the results using the trapezoidal rule are good. So you see it was good here, and in practice it's even better. And k can be any number larger than all the values of f double prime of x in absolute value, but smaller values give better error bounds. So sometimes this is what I will ask you to do. I do ask problems dealing with this on assessments. And in fact, we're not going to just go to assessment. You get to practice this now. So how large must we take in order to guarantee that the trapezoidal and midpoint rule approximations for this are accurate within, and that is tenths, hundredths, thousandths, 10,000ths, 1/10,000th. You know what to do. Let's see how you did. Okay, so now we knew already from the discussion that f double prime of x is less than or equal to 2, and we want the error to be accurate within 1/10,000th. So we put 1/10,000th here, and the error I put on the other side. So this is the trapezoidal one. So this is 2, 1 cubed, 12 n squared. Now you have to solve this inequality for n. So we cross multiply and we get this, and we take a square root and we get this. So that means n has to be bigger than 40.8. Now, since n is an integer, you have to say, oh, I need 41 terms. This is a very important engineering question. If you need an answer within a given tolerance, how long do you have to let your computer program run in order to get that? You see, you don't have to know the exact value. And if we do the same thing with the midpoint rule, what we get, now notice there's a 24 there now, so we solve that. But you see, because of the square root, you are getting a lower bound here of approximately 29. So the midpoint rule is a little bit better, but it's not as simple as the trapezoidal rule, and so there is a trade-off. And again, we should note that it's possible a lower value actually could happen, but 41 is the smallest one that comes from the trapezoidal rule, and this is the one that comes from the midpoint rule. Let's do another one. Now this is the problem that we talked about at the beginning of the last lecture, and you don't have an exact answer here, but this is the integral from 0 to 1 of e to the x squared dx. Use the midpoint rule, this time with n equal 10. Actually, we did that. We did that at the beginning. But here, what I want you to do, let's just do part B. Give an upper bound for the error involved in this approximation. You know what to do. Let's see how you did. Okay, so this is just part B. So what I do is I take the function is f of x is equal to e to the x squared. F prime of x is 2x e to the x squared, and f double prime is, and you should verify these calculations, but since 0 is less than or equal to x less than or equal to 1, and x squared is less than or equal to 1, we have that 0 is less than or equal to f prime of x because you're multiplying positive numbers, and this is going to be less than or equal to 6e. That means we can take k, the maximum is less than or equal to 6e. And so we take k to be 6e, that is a number. A is 0, b is 1, n is 10. We do the calculation, and this is for the, this is the midpoint rule because you have 24 there. So that is e over 400, and if you plug that into your, this is the exact estimate of the error, but that's approximately this. So error estimates give upper bounds for the error. They are theoretical worst case scenarios, and the actual error in this case is actually smaller than. Actually, it's not smaller than this, but this is comparison with the trapezoidal rule. Now we're going to start talking about Simpson's rule, and Simpson's rule is even more powerful. And I will, at the outset, say this is quite an excellent approximation. 300 years after Simpson, I am still using an adaptive Simpson's rule when I do my math. So we're going to talk about this, but this is a different approach. So instead of using straight lines or trapezoids for this, we're going to approximate by using parabolas instead of straight line segments. Now, a parabola is going to have ax squared plus bx plus c. So the capital A, capital B, and capital C are unknowns. So, but if you have 3 points, you can find the coefficients of the parabola by solving 3 equations and 3 unknowns. So this is what happens. The blue is the curve, and we say, oh, through 3 points, we're going to draw a parabola. And then through the next 3 points, we're going to draw another parabola. And through the next 3 points, this one, this one, this one, we have it. But notice that in the trapezoidal rule, we had one of the sides, one of the bases of the trapezoid kept getting repeated except for the first and last. Now you see what happens is this P1 is involved in the first one and the second one, but other P1s are going to be involved in actually 4 of these. So this is what we're doing, is we're approximating by parabolas, and then we need to find what is the area under the parabola. And we start by saying, well, what's the area under the parabola? So if P of x is equal to ax squared plus bx plus c, what is that? Definite integral from a to b, where a is one end and b is the other. Well, we can do the calculation, but we'll end up with something that looks like this. But let's actually go through the proof of this. This is a theorem after all. So we're going to be using this thing. But notice this says we have b minus a over 6. This is the parabola's coefficient evaluated at the left endpoint. This is the parabola evaluated at the right endpoint. And this is 4 times the parabola evaluated at the midpoint, or the average between A and B. Now this is actually very interesting computationally, and here's the proof. So we're just going to calculate the integral of P of x and see that that's true. So if we integrate from A to B P of x, we get the integral from A to B. This is ax squared plus bx plus c dx. We do the integral, and we plug in the answers. And then we do some rearrangement here. And we factor out, this is algebra, you factor out the b minus a over 6, and you're left with this. But if you check, you see that you have the b of a, b minus a over 6 on the outside. But when you look at this, you see that this expression, when you simplify it, is p of a, 4p of a plus b over 2, and p of b. So that is the proof of this little exercise. And you should make sure that you understand these calculations. But now, what we can do to do Simpson's rule is we can look at each of these subintervals. So this is the integral from one point to the subsequent point, f of x, but we're approximating this by the polynomial. And we get this by that little theorem, which can be organized into this. So what you see is we end up getting b minus a over 3n, regardless of what interval it is. And then we get f at the left endpoint plus 4f at the middle point plus f at the right endpoint. So this is what Simpson's rule says then if we add these together. Let f be continuous on AB, and let n be an even integer. This has to be an even integer so you don't run out of points. That's not really a big constraint, but it is important to remember that for Simpson's rule, n has to be even. And then the approximation is this. The integral from a to b of f of x dx is approximately b minus a over 3a. And notice what happens. This endpoint is by itself. This endpoint is by itself, but because we're using the parabola, we're alternating here 4, 2, 4. Keep alternating 4 and 2. Your last one is 4, and then you go back to 1. And as n tends to infinity, the right hand approaches the definite integral. So observe the coefficients work according to this pattern. It is 1, 4, 2, 4, 2, 4, dot, 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 4, 2, 4, and 1. Now, more complicated, but let's see how it will work. So as an example, we're going to go back to a problem we did before. This is the integral from 0 to pi of sine x dx, and we know that this is 2. But now we're going to use Simpson's rule for n equal 4 and n equal 8. When n equal 4, you get something very close to 2. When n equal 8, you get something even closer to 2. Now notice that these are tighter than the estimates we saw with either the midpoint or the trapezoidal approximations. And in fact, this is the error estimate. So, and it's a more complicated thing because it's higher technology, but I'm also going to tell you that this is what I actually do in my math work. Moreover, if f has a continuous fourth derivative on the closed interval AB, then the error in approximating is the absolute value that you could have called this E sub s if you want to. This is Simpson. This is b minus a to the 5th, not the 3rd, but the 5th. The denominator, comparing it to trapezoidal rule, is not 12n squared, but this is 180 n to the 4th. You see, when you think about this, you conclude oh my goodness, this is a tighter estimate. And k, again, as before, is going to be the max of, and this is the max of, the fourth derivative of x, as x runs from a to b, the closed interval. So this is your error estimate for the trapezoidal, or excuse me, for Simpson's rule. This is for the trapezoidal rule. Now, in many applications of calculus, you need to evaluate an integral even if no explicit formula is known. So for example, suppose you did measurements of something and you found that, in fact, let's think about what we're doing here. So in this case, what we're doing is we're looking at data traffic on a link. And this is a communications link. And this goes to Switch, which is the Switch Academy and Research Network. Okay, so this is the data that goes. D of t is the data throughput measured in megabits per second. We're going to use Simpson's rule to estimate the total amount of traffic on the link from midnight to noon on that day. Now you see, you just get a bunch of data points that you have, or measurements. So this is what D of t was at time 0. At time 1, and they change it to seconds here, this is the traffic. This is the traffic. This is the traffic. So you see you have a whole bunch of data points. This is for values of t. You have d of t. But this is the only thing that you are using in Simpson's rule in this example. You don't really need the entire curve. Okay, so this is what we're going to do. And so the integral from 0 to 43,200 d of t, that's going to be the total amount of traffic. Okay, so that's the amount of data that's transmitted. Well, we use these data points. And we plug in. So you see, we can say delta t over 3, and an hour is 3,600 seconds over 3, and we just plug in all these values. Now notice we are using the pattern 1, 4, 2, ... 4, and 1, and we use that with all of those numbers, but we can do the calculation and get this. I think you should notice that Excel would be an excellent way to do a problem like this, and you will have Excel access during the assessment. So this is important, and I actually like these kind of problems. And let's go back to a problem we did earlier too. How large should we take in order to guarantee the Simpson's rule approximation for this integral is within, and that's tenths, hundredths, thousandths, 10,000ths. Well, you see in this case, f of x is 1 over x, and if you take all the fourth derivatives, you get 24 over x to the fifth. But again, we can conclude that the absolute value is less than or equal to 24. That means k is 24. And so we can substitute into the error formula, taking this to be the maximum error we'll allow, and we'll solve for n, and we find that n is approximately 6. You see, this is dramatically a smaller value of n. And actually, we can't take n to be 7 because it must be even for this, so we take n to be 8. But still, that is much better than the 41 and 29 that we had before. And again, this is a kind of problem that I often like to ask. Here's one for you to try. Use Simpson's rule with n equal 10 to approximate this integral. Now this is an integral we've studied before, but you can't find the exact value. You don't need to, but you're also going to be estimating the error found. Now, even though we did this using the midpoint rule before, we haven't really done it using trapezoidal rule, and we certainly haven't done it using Simpson's rule. So you really should do both of these. You know what to do. Let's see how you did. Okay, here is the work, and you should check your work with this. And so we get that the error is approximately, and you can see that this is much smaller than what we have Actually, this is the value of the integral, excuse me. This is the value of the integral that we get is this one up here. That's the value of the integral. But then this is the error statement that we get. So the value of the integral by Simpson's rule was 1.46 and change. That's this one over here. And this is the error statement. In closing, now more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now more than ever, take care of yourself and of each other. We're all in this together. May God bless you all.